In this video, I will show you how batteries work, what is wrong with lithium-ion batteries, and what can be done to improve them. Prepare for a short fragment of school knowledge. Batteries convert chemical energy through redox reactions into electrical energy. In theory, they consist of several electric cells. However, a single cell is also often referred to as battery. A cell should have an anode and a cathode immersed in an electrolyte with a separator that ensures the electrodes do not touch but allows for the ion exchange all within some sort of a container. I will illustrate how the cells work on the example of one of the most popular ones, which is a galvanic cell. In a galvanic cell, the cathode is a copper plate with anode being a zinc plate. Because the half cells are in two separate containers, there is also a salt bridge filled with electrolyte for the ions to flow and to allow for charge exchange. To close the circuit, there is a wire connecting two electrodes through which electrons flow. The anode is a place where oxidation reaction occurs and electrons are released from, while the cathode is a place of reduction reaction and where the electrons are accepted. As the standard electrode reduction potential, it's hard to pronounce. By the way, it's just a measure of ability to undergo reduction. So, as this potential is high for copper, copper 2 plus ions undergo reduction to copper atoms. Zinc atoms at the same time are oxidized to cations with 2 plus charge. These reactions result in the flow of electrons, which is basically the electric current, since current is an order movement of electrons. Reaction in a galvanic cell occurs spontaneously because its Gibbs free energy is negative. In some of the cells, it is possible to reverse the reaction when providing electricity. When the reverse reaction is possible, the cell is called a secondary one, and when it's not possible, a primary one. Lithium-ion battery cells are secondary cells. What is important for later is what can go wrong. So basically, how do batteries break? Batteries, as lithium-ion ones, derogate with time through various defects, such as dendrites formation, electrolyte breakdown or leakage, and damage done to electrodes, including the volume change and cracking. Factors increasing the probability of damage done to the battery include extreme temperatures, repetitive full charges and discharges, as well as number of completing charging cycles and the age of a battery. Now, knowing the basics, meaning what batteries even are, let's talk about the most popular type of batteries, being lithium-ion ones. Lithium-ion batteries have a high energy density. Compared to alternatives, their cycle life is quite decent. About 500 charge cycles, but in proper conditions, it can be even up to 2,000, 3,000 cycles. The numbers, though, vary a lot depending on the source. Their another advantage is fast charge and discharge. Also, they can have high voltage and not heavy. Their popularity seems to be justified. But lithium is a scarce resource. As demand for lithium-ion batteries is only expected to grow, it becomes a problem. Alternatives are being developed, but each of them faces their own challenges. It seems that we should put some of the attention on the improvement of existing lithium-ion batteries. One way of enhancing batteries that caught my attention is to incorporate self-healing materials into battery components. I like this idea because of the possibility to transfer the solution later to other types of energy storage. self-healing materials have the ability to, you guessed it, self-heal. Meaning they can repair themselves either autonomously or when triggered by an external stimulus. For the self-healing properties to occur, there have to be some reversible interactions between the molecules. Self-healing materials can take advantage of supramolecular interactions and dynamic covalent bonds. Supramolecular interactions include pi-pi stacking and hydrogen bonding. The interactions are easily re-established after the molecules are split. Pi-pi stacking is basically overlapping of pi orbitals of aromatic rings. Dynamic covalent bond is a reversible sharing of electrons between two atoms dependent upon particular factors, which, depending on the dynamic bond, can include the pH, light, solvent polarity, and temperature. Stanford has already tested using self-healing materials in battery components. They used self-healing conductive composite as a layer on the anode's silicon microparticles. Batteries made using this technology had 80% of the initial capacity after 100 cycles with 10 times the duration of the possible battery usage. Self-healing materials used in electrolytes or electrodes of lithium-ion batteries could not only prolong the cycle life but also increase safety of battery operation. Moreover, they give an opportunity to use new materials in batteries that were too easily damaged to give positive outcomes when not joined with self-healing materials. For example, silicon anodes that have 10 times the capacity to store lithium ions compared to a graphite anode were not frequently used because of the drastic volume change and easy damage that can be reduced using self-healing binder. If you are interested, you can check out my article on the topic. So, why don't all of the batteries have self-healing materials in their components? There is a challenge to optimize self-healing properties with other ones crucial for battery operation, such as conductivity or energy density. There is an issue of compatibility with other substances, the appropriate method to apply the self-healing agent, and the cost of the produced battery. Generally, self-healing materials create a big opportunity to improve lithium-ion batteries and other types of energy storage. However, there probably is an equal need to make advancements in other areas of materials improvement, production methods, and recycling. Thank you so much for watching and see you next time. Bye!